Hello, everyone. Welcome to my talk. I'm Laptev, and I'm directing research at INRIA in France and at VisionLabs. Today, I'm going to talk about promises and challenges of visual artificial intelligence. So let's first quickly see what is visual artificial intelligence, or in more classic terms, what is computer vision. So on this video, you see a matrix of numbers, which is obtained from a video camera, which represents an image or video. And the goal of computer vision is to first understand that this matrix of numbers actually corresponds to a real video, and then, of course, also to understand the content of a video, for example, in terms of objects, people, scenes, human actions, and so on. So this is obviously a very difficult problem, which people have been working on for quite some time. And recently, we've seen lots of interesting progress, and I will just show a few examples to illustrate. So here is a video where a recent object detector is run real time, and it's able to detect around 9,000 different object classes, and it does it pretty well, as you can see. So here is another example which appeared recently, where you see that normal RGB video without any depth or other data, the algorithm is able to detect people and also to delineate their poses, so basically finding the joints of different people in real time and for complex scenes like this one. So here is another example which is quite famous. I guess you know about this. So DeepMind has beaten the AlphaGo Masters in around 2017, which is a obviously very difficult task. And so although this is not a computer vision example, it's still interesting in this context because the algorithms which were used to solve this task were actually computer vision algorithms, where the board of the game is represented by convolutional neural networks, which is very similar to standard vision techniques which are used nowadays. So what's also interesting is that all of these examples, they just appeared recently. In particular, the three examples which I've shown, they all been out since 2017. And around this time, there's been lots of other interesting work appearing. So the interesting question is what happened? So why this breakthrough just happened recently? And of course, what will happen next? So what should we expect in terms of technology, in terms of applications in the near future or maybe in the far future? So to look in the future, it's probably always good idea to look at the past first. So let's do this. So the early days of computer vision started as a summer project at MIT around 60s. And people quickly realized that this goes far beyond the summer project. And there've been lots of research since then. Of course, in the beginning, the scenes were very simple. In terms of algorithms, the first neural network, which was actually algorithm neural network, was in 57. The perceptron algorithm. Later in 80s and 90s, convolutional neural network appeared, and actually they were working well for simple images such as digit or characters, and there were real applications of this technology. Then recently in 2012, more things happened. And although algorithms more or less stayed the same, what we've got much more powerful computers, in particular GPUs, and we also got lots of data. And so by coincidence, all these components suddenly enabled lots of progress, which then transferred to many applications such as autonomous car driving, face recognition, delivery. There's lots of progress in medical imaging and in many other fields which are using vision. Let's see a bit more inside these neural networks, which are state of the art and which are doing the job nowadays. In particular, what are the ingredients of these methods? Of course, there is a neural network itself, and there is lots of work going on it, both to construct the better representations and to understand what is happening inside. But apart from the neural network themselves, the important ingredients, of course, the data, the computing power, and not least the supervision. So supervision is, for example, here on the right, you see images annotated by regions of objects, and you can imagine that such supervision is quite expensive. So indeed, to construct sufficient data set to train neural networks, we need lots of labeled images, which is currently working the best, so-called supervised learning. So for example, MS-Co code data set has annotation for 80 object categories, around 300,000 images, and 2.5 million of labeled objects. And so these took about 60,000 of human hours to annotate, which is a lot of job. But then if you see it in perspective of the total amount of data which we would like maybe to recognize, this is still a very, very small part of it. So obviously, like 80 object categories is not sufficient. And if you want to go much larger scale, then the supervision or manual annotation really becomes a bottleneck. And so here, well, apart from that, it's just expensive. Sometimes it's a questionable whether we can even do this annotation at all. So here are 3 examples where we can pose this question. Like on YouTube, there are thousands of years which are uploaded. I don't know how much frequently, maybe every week or so. And annotating the video is a very demanding task. So annotating it at scale is almost impossible. And then there are fields, or there are subfields like 3D object reconstruction, where the 3D, unless you have a 3D camera, which also has its own limitations. So if you want to get ground truth for 3D, for say hands and objects in any videos, this is not even possible to annotate manually. Another important and interesting area is robotics. Robotics needs perception, means vision, and the output of robotics is not labels for images or 3D reconstruction for images, it's actions. So we want to actuate the robots to perform interesting tasks. And here, what are the forces should we? Here, the manual annotation seems not possible at all. Right, so to finish the part of the overview, so what I wanted to say is that, so indeed, we have powerful technology, which has shown lots of progress recently because of computing power, algorithms, and the data. However, so for the future, we can expect that computing power will increase. So we will have more interesting architectures to recognize images. However, if we rely on supervised learning, in particular, manual annotation for supervised learning, this is going to be a bottleneck, which will prevent us to going further. So my research actually goes towards direction of learning neural networks, learning computer vision to deal with less supervision or with no manual supervision. And these three subfields, which I've shown in previous slide, actually happen to be also 3 directions of my research. Unfortunately, in this talk, I won't be able to talk about all of them, but I will particularly focus on automatic video annotation and how to do this without using any manual supervision. So let's dive into this work, which was presented in CVPR 2020 this year. So it's a joint work between INRIA and DeepMind. So the starting point for for this work was data. So data here is our instructional videos. You may have encountered instructional videos when trying to learn how to, for example, how to change the car tire. If you have never done it before, of course, you can look at manuals, but now there is an easy way. You type it in internet search, and immediately you get lots of videos with people showing you how to do what you want to do. And they not only show it, they also describe it. So there is a narration. And so the goal of this project and also the line of work which we've been doing for the last few years is to use this data to automatically learn computer vision, how to understand what happens in the video. And the crucial moment here is that apart from the video, we also want to use the narrations. So you can see transcribed narration here. And also you see that it's not available just for one task. So it's really available for many tasks. There are lots of different videos for different tasks. So you want to use this data, and you want to use narrations as a supervision for video understanding. So the scale of the data recently can be very large because for some reason there are lots of how-to videos on the internet. People upload it without thinking that this could be useful for us, for computer vision researchers. But there is lots of this narrated data. So with quite limited effort of actually just 2 students in a few months, we were able to scrape. So we started with WikiHow, which defines lots of different tasks. And then given the names of tasks, which were obtained automatically, we went into YouTube, collected more than 1 million of videos. We split them into short parts and obtained about 130 million of video clips, which are not just video clips, but they also accompanied with narrations. So narrations describe what happens in the video. And importantly, so this data set covers many different domains like cooking, vehicles, home tasks, and it has really 0 manual annotation. So we are not relying on any manual labeling, and that's what makes it approach scalable. It's already at a large scale, and it can be scaled even further. So just comparing it to previous data sets, so our data set is about 1,000 times larger. It's less precise because previous data sets have been annotated manually, and they are much more accurate in terms of labels. Our data set is automatically collected. So let's see what we can do with this data. Here, a simple, quite straightforward task. In people working with vision and language will recognize it immediately. One thing we can do, we can try to learn so-called embedding or feature space for the narrations, for text track, and for video. And we want to learn in such a way that in a joint feature space, the videos and corresponding narrations, they are close to each other, and videos and narrations from other videos which are not corresponding to the target video are far away, right? So this is a standard joint embedding learning problem, which is known in computer vision and also now language. Or so in terms of the method or architecture, maybe there is not much new novelty. However, there is an important problem here that can be illustrated, that narrations, because they are not manually annotated, so if you just take narrations which timely correspond to the videos, so we often see that there is no correspondence or weak correspondence because people do things or show things, and they may talk about this either before or after they actually do it. So in this example, we actually see that the objects or actions which are present in the video, they happen before or after the video clip itself. So we want to deal with this imprecision of our automatic annotation, and we do it by proposing a multiple instance learning contrastive loss, where during training, we try to associate, we take all the narrations which are surrounding the video clip, and we try to associate only the correct ones with the video, and incorrect ones should be automatically filtered out. For this, we propose a multiple instance learning contrastive loss, which is different from standard contrastive loss by the fact that we are summing over all narrations. So G is narrations here, and F is a video. We are summing over all narrations surrounding the video clips which we are looking at. And this simple, quite straightforward method enables us to, on a large scale, enables us to filter out during training the wrong pairs and to focus on the correct ones. Of course, there's not much time to go into details. Details are in the paper. Just, okay, and then for negatives, we just sample the pairs of videos and some non-corresponding text randomly, and yeah, summing over as many negatives as possible. So network architecture is quite standard. So we have some architecture for text. We have a 3D scene architecture for video. And here, importantly, we learn it really from scratch. We are not using any pre-trained network, for example, which would be pre-trained on our data. Results. Interestingly, what we see here is that learning on our large-scale data using the proposed laws, for the problem of text-to-video retrieval, it outperforms other methods which were trained on manually supervised data. We see similar picture for other problems such as action recognition. So here are a few different methods and 2 data sets. And so on a variety of problems, we observed similar behavior, that we learning from this large scale, not manually annotated data, our method is able to outperform other methods which were trained on manually supervised data, but which was on a much lower scale. And this is significant because typically in computer vision, you see weakly supervised or self-supervised learning methods which are trying to beat these fully supervised methods and not reaching it quite, because it's hard to learn from noisy labels. In our case, we actually can do it probably because of the loss of the new laws, and also because of the so much more data which acts as a denoising to denoise the errors in itself. Right. So in this video, you see quick results of what we can do. So here's a quick search demo where you can type anything and search the UCook videos, the UCook 2 dataset. Actually, this demo is online. If you want to try it, there will be a link on the next slide. So you see here that our queries can be quite detailed in terms of color, in terms of actions, in terms of quite specific objects which are considered. So the code and the pre-trained models are actually available. If you want to try it, please go to this website. You will also be able to test this demo, which I've just shown. The models, pre-trained models, they're state of the art. So if you want to do something with video understanding, using our pre-trained models is a good start. And to summarize my talk, so back to the slide of the overview slide over time. So what I mentioned earlier is that, yes, we do expect lots of progress. However, the manual annotation is a problem at the moment. And I've shown you an example where manual annotation can be avoided. I believe this direction is very fruitful, and we will see much of this work happening more in the future for different fields, not only for video understanding, but also for other fields such as robotics. Thank you very much for listening.